Again, back from lunch. Welcome to the Jagged Edge streaming end-to-end encryption with Aage in Java and beyond. And if you were here earlier, but I'll reintroduce myself again if you weren't. I'm David Hanneman, a PMC member on the Apache NiFi project. I've been a committer for over 3 years, so everything from extensions to framework code to anything security, encryption, authentication, authorization. Lots of fun there. I'm also a software engineer at Datavolo, which is powered by Apache NiFi. And I run a software development blog at exceptionfactory.com where I write about Apache NiFi development, other open source contributions, and development best practices. So this afternoon, I'd like to talk about Aage encryption and cover a few aspects of it. First, just what is Aage encryption at all? Maybe you've never heard of it. If you have, great. If not, hopefully it'll be informative. And two, what is Jagged, which is, spoiler alert, the Java version, Java implementation of the Aage standard. So I'll provide a few samples and some of the details there. And then where is Aage available? What languages, what frameworks, what applications, and hopefully wrap up with a short example of how it's used in Apache NiFi. So first, what is Aage? It's a modern file encryption format supporting pluggable recipients. So I'll unpack that a little bit. First and foremost, the name itself. The author says on the README, he pronounces it with a hard G, so Aage, not age, but as many things go, the pronunciations in the eye of the beholder, perhaps. The authors are Filippo Valsorda and Ben Cartwright-Cox. Filippo Valsorda worked for Cloudflare, Google, and he's currently a full-time open source maintainer, specifically working on the Golang crypto library. So he has a great blog. I highly recommend it if you're into anything security related. Very interesting read. And he also has some background on why he developed this to begin with. Speaking of the implementation itself, the reference implementation of Aage is written in Go. There is both an API, if you want to consume it as a library, and the easiest way is a CLI. I'll provide some examples of that. So Aage is a streaming authenticated encryption format. That means you get authenticated encryption. There's two kind of popular algorithms for that, probably the most popular, obvious, AES and GCM mode. And then the other one, which I'll mention in a moment, which Aage uses. And then it's streaming so that you do not have to buffer the entire input or output into memory in order to get that authenticated encryption, in order to do that integrity checking that's part of the authenticated cipher. So I'll unpack that a little bit more. I should also caveat, I am not a cryptographer, so fair warning there. If you want to know about the advanced math, that's beyond me. But one of the positives and one of the reasons Aage was built on standard algorithms. So there's RFCs, there's standard implementations of these algorithms in most languages. So it's not like we're reinventing the world here, which is important when it comes to cryptography. Aage also supports two basic native recipient types. You can do public-private key pair encryption or password-based encryption. And this is the one pluggable extension point of the specification. So it is an open specification. If you go to aageencryption.org/v1, it'll redirect to the GitHub repo that has the nitty-gritty details of the file format, the encoding details, the algorithm applications, how each key is derived. So it's, again, into the details. If you can follow those basics, it's fairly approachable, unlike some other formats. It's still details to understand, and having the reference implementation is important, but at least it gives you something to start with. So just a quick overview of those algorithms. There's one cipher algorithm, the Cha-Cha-20 Poly 1305. Again, if you haven't heard of it, it is not as commonly known perhaps as AES, but it is one of the two cipher algorithms that are supported in TLS 1.3. So again, if you follow TLS, you know TLS 1.2 and earlier had dozens and dozens of cipher suites, all various combinations. TLS 1.3, it's down to less than 10, and only two authenticated cipher algorithms, of which Cha-Cha-20 Poly 1305 is one. So there's that, again, official basis. There's an RFC for that, implementations in most languages. The public key algorithm is X25519, so it's an elliptic curve cryptography algorithm, unlike The more historical RSA format, again, I'm not a math or cryptography person, but the basic difference being it's not based on prime numbers and exponentiation. It's based on points on a curve and deriving the public and private key based off of that. So the net result from a consumer or developer point of view is you get much smaller keys, but you get the same level of security from, at least according to cryptography research. It's also worth noting that both of these algorithms were created by Daniel Bernstein, an expert in the field, and again, if you really want to dig into the details, can be interesting. The password-based algorithm, Scrypt, it's been around for a while. There's an RFC for that. It's used in other cases for key derivation or protection against brute force attempts. And the basic summary there is it's both time, CPU hardened, and memory hardened in terms of the more you tweak the parameters, the strengths, or the work factor, it'll cost more CPU time and more memory time, so it's more resistant to brute forcing than certain older algorithms like PDKDF2 and others. And so again, back to the standard itself, there's one extension point, the recipient type. So those are the two native types. You can plug in others, and I'll mention one of the primary ones that the Go implementation provides. But there are no other parameters. So this avoids things like algorithm attacks or passing in something that a library may interpret and thus downgrade the security. I'll mention that a little bit more. And then there's two file encoding types. There's the standard binary format, which has a textual header, which we'll look at, and then just the binary encoded, encrypted bits. And then there's a base 64 encoding using the traditional PEM begin and end footers, and then a base 64 blob. Another important and valuable thing about this as an open specification, there's a whole set of test vectors. So there's the GitHub project. If you are interested in exercising the AGE encryption standard, or you're interested in evaluating the library, this is a very helpful set of test cases. It includes not only positive tests, but a number of negative test cases. So things like padding or invalid arguments for certain recipient types. That's all in there, so there's over 100 positive and negative test cases. I was able to use this in the process of developing the Java implementation, and it's, again, a GitHub project, easy to verify, easy to understand the format of the spec itself. So a little bit more background. Again, it's worth reading if you really want to dig into it, some of the motivations why the authors developed the standard. First, one of the primary motivations was an alternative to OpenPGP for file encryption. Emphasis on file encryption. It's not a digital signature tool. It's not going to be a replacement for Git commit signing or release signing or something like that. It's only for file encryption. And emphasis on also the streaming and simplicity factors of the standard. Streaming was an important goal, so whether a file was a couple hundred kilobytes or into the gigabytes, the idea that you could encrypt and decrypt without using huge amounts of memory, but still have that authenticated encryption and integrity checking built in to the algorithm itself. Again, other motivations, standardize on modern algorithms. OpenPGP is great. It's been around over 30 years in some incarnation. And with anything, you get historical and thus less secure algorithm support, things like Cas5, RC4, triple DES. Some of these are completely insecure, some of them might be secure in some cases, but the cryptography world has moved on, and so baselining on only modern algorithms was another key design principle of the specification. And then one of the things that's not part of the official spec, but it's supported as a first-class capability in the reference implementation and in other implementations, is encrypting to SSH public keys. So as with anything, adoption, the author intended to provide some ways to get over initial adoption hurdles. And so key distribution being a challenge, GitHub with its standard capability to publish SSH keys with which you're signing your commits, has those keys available. So what you're able to do with the AGE CLI is make use of those to encrypt to a recipient just using their SSH public key. If you want to go into the details, that only means SSH RSA or ED25519 keys. There's other algorithms that are not supported, but with those caveats, it is nice and easy to take a SSH key pair that you may already have and then use that to encrypt to a recipient. And then last, like I said, avoiding those algorithm negotiation issues. An example of this is the Jagged, or the JSON Web Token Standard. If you've followed any of this in your recent history, the fact that the standard includes an algorithm header and none was a valid value, so many library implementations allowed that without any customization. So there's been CVEs around that in various libraries, and thus changes to make development be that make that an opt-in option versus having it as a supported feature by default. So avoiding some of those algorithm negotiation features, it was another core design principle of the spec. So a little bit of example from just the CLI to get an idea of what this actually looks like in its most basic form from an end user kind of consumable point of view. There's two basic commands, AGE and AGE keygen, which exactly as they sound. One's for key generation, one's for encryption and decryption. So in order to do encryption with a public-private key pair, you need to generate a key. So the AGE keygen command, very simple. If you run it with no arguments, it'll print the public and private key to standard out. If you run it with -O, give it an output file, you get the private key, and the public key is a comment, but you get the public key also printed. So very easy, just very similar to SSH keygen in that way. Then for encryption, fairly straightforward. AGE-E for encrypt, -R for recipient. You pass it one or more public keys. I'll get into the format of that in a minute. That's a truncated example. And -O, the output file, the encrypted file. And then the last is the input unencrypted file. You can also use standard Unix composability pipe to AGE command, and it'll read that, thus the streaming capability is write it to that output file. Decryption, going the other way, same basic principle, -D for decrypt, -I for the private key, -O to output the unencrypted file, and then followed by the encrypted file as the input. So taking a look at what the file itself looks like, the binary part, not much fun to look at. We'll see an example just of the hex encoded NiFi later on, but here's what the header looks like. So the basic couple lines, it's semi-human readable, mostly base 64 encoding, but there's three basic parts in the header itself. So you have the version line, ageencryption.org/v1, giving some opportunity for future iterations if there's a version 2. Very easy to differentiate that. The next and probably the most important part from a header point of view is the recipient stanza. So that's always begins with that -- sign space and then the recipient type. Now there was some confusion. You can read some blog posts about this. Are you specifying the algorithm as in the value there? Well, no, it's not the algorithm, it's the recipient type. It just happens to be the algorithm name as well. So it basically says this is the public key type, and then here's an argument to that. And then the last bit of the header is a map, so followed beginning with 3 dashes and then base 64 encoded bytes. So basically after you've read the header, the standard will compute the file key, which is derived or present from the recipient, and then you can verify the integrity of the header. And there's a little bit of chicken and egg problem there in terms of reading the header. Do you trust the header? But at least after you've read the header, you can, before you're decrypting the body, you can verify that the header hasn't been changed. In the payload, no real visualization there, but the two of the main things to take away there are the random nonce, so use only once from a cryptographically random source, 16 bytes. That's used to then compute the payload key used for the actual cipher decryption process. And then the payload itself is one or more chunks of 64 kilobytes. So this is where the streaming aspect comes in. If you have something less than 64K, it's going to be only one chunk and you're done. If you have more, you keep incrementing a counter, and that goes into the nonce for the decryption or encryption or decryption process. And that's put together with the payload key to encrypt or decrypt whatever you're doing. So again, that gives the authenticated encryption part, so each 64K chunk gets integrity checked as it's streamed through, rather than having to buffer the entire thing. So on to the Java-specific part, Jagged. Tongue-in-cheek in a few ways, the dangers of doing anything cryptography related. If you've ever done anything with the Java cryptography architecture, you know it's not the easiest API to use, has some potential foot guns. So the purpose of the Jagged library is to kind of reflect that a little bit, but also as I've developed it, I've tried to follow some encapsulation, try to call out crypto-specific things versus format-specific things. But with that, at the time I was looking for an implementation. There was nothing in Java. There was a work-in-progress implementation for Kotlin, which could be used in Java, but there was no native Java implementation. So a little bit about the Java implementation itself. You can find it on github.com, my username exceptionfactory/jagged. As an exercise in math futility, sometimes fun, sometimes pain. It supports Java 8 through 21. For Java 11 through 21, you have no additional dependencies. This is because in Java 11, Java added support for both the Cha-Cha-20 Poly 1305 cipher algorithm and the X25519 key exchange algorithm. So that has the benefit, if you're running on those versions, you don't need any additional dependencies. If you're still stuck on Java 8, you can run a Jagged with the Bouncy Castle security provider. So this is part of all the build tests. Optionally brings in that dependency for running the tests on Java 8. And so you can either call that programmatically, instantiate the class, and instantiate the relevant portions, or you can go into the Java security configuration, set your providers. Your mileage may vary, but it's capable. Then I also made sure that there were extensive unit tests and making use of those community cryptography test vectors, and all those pass. I also spent time modularizing the design, so maybe a little excessive, but for reasons of security and also for evaluation. There's the core API, which is very minimal, couple interfaces, couple classes. There's the framework, which has the bulk of the crypto code and also the format handling, the header parsing, header reading, all of that. But I separated out the recipient type modules. So if you only want to support the public-private key pair recipient type, the X25519, you only need that module. If you only want to support password-based, you only need the script module. And SSH, its own thing. That's several layers of interest, as SSH keys have different types of formats as well, but that's modularized. So it gives you some selection and some isolation of issues there. A little bit of a sidebar, Bec32 is another thing mentioned there. It's a base 32 encoding, not base 64, so a 32-character alphabet. Comes out of this Bitcoin Improvement Proposal 173. You can go and look that up if you're really bored. But it's basically 3 parts, and it's a string. So you have the human readable part saying, what is this? And Agge uses that. There's either Agge or Agge secret key for public or private key. There's a separator, which is always 1, and then the actual data with ending with a 6-character checksum. So really in the weeds, but there's, again, implementations in other languages. There wasn't one cleanly available for Java, so that's what that module is. And it's in support of those public and private keys for the X25519 recipient type. So there won't be too much Java code, this slide or the next one, but here's an example of generating a public-private key pair. So you just instantiate the key generator, implement key pair generator, implements the Java security key pair generator, and then you get a wrapped instance of the public and private key. And in this case, I'm just printing out the value. So if you do a 2 string, you get the Bec32 encoded string. So there you can see that human readable part. Public keys are always lowercase. Always starts with Agge, the number 1, followed by the actual key. The private key, similar, except it's all uppercase, starts with Agge secret key. The actual encryption and decryption process leverages Java NIO. So again, trying to lean into the streaming capabilities. The implementations provide a writable byte channel for encryption or a readable byte channel for decryption. There is a standard implementation, which supports the binary format, and then an armored implementation supporting the base64 encoded version. As with anything, an additional layer takes more work, so if you don't need the armored ASCII base64 encoding, it's much more efficient to use the binary form, but that's an option. Then the two recipient type interfaces, you have the recipient stanza writer, which basically takes the file key and returns a recipient stanza, and then the reverse of that, for decryption, you need to read the recipient stanza and return the file key to do the encryption operations. So there's implementations of that for SSH, for script, for X25519. The last bit of Java code, again, it's hard to capture everything on a slide rather than going out to the IDE, but this is a basic example. If you look also at the project, you'll see some more code samples. But basically, binary encryption with that public key, get that public key from somewhere, create a recipient stanza writer by passing in that key, and then having that channel factory to then take your source and your destination. So this, just using the Java NIO files, pass the file path for the input, pass the file path for the output, and then you could have a list of one or more recipients, depending on if you're just encrypting to one, you only need one, but the spec allows multiple, so you can take it will take a collection there. And the copy method, just passing on to basically using the Java NIO byte buffers to read and write, and do that iteratively until you're done. So now some examples of where you can actually use it, how you can integrate it, and then we'll wrap up with where it's usable and where it's built in for Apache NiFi. So multiple platforms, multiple languages, multiple projects, lots of community involvement and open source integration in various places. So for the CLI itself, there's actually packages for all popular OSs. You can do a brew install on Mac OS. I mentioned Ubuntu and Debian app install, but it supports Fedora, Gentoo, just about all of the popular Linux distributions. Even Windows, there's a Chocolate package manager, so you can do it that way. There's Scoop and others. So most distributions are available and supported by the reference implementation, the reference CLI that's written in Go. So they've just done a great job and gotten good community support on the packaging side to make it available across platforms. Multiple languages. So here, this covers most of them, or most commonly used ones. Of course, there's more. On the left side, I put both the reference implementations and my own, as well as the more polished ones. On the right side are more work-in-progress languages. If you go to, or if you just search for awesome Age, the author maintains a list of languages, implementations, all these details. So that's on GitHub as well. But again, just to recap, there's Go, there's Java. Rust is a close to a reference implementation. It's reference on the Go side, but that's regularly maintained, has feature parity. Python, so there's a PyRage, it's wraps, it's a Python binding, so it's not implemented in native Python, so it's actually the benefits of the native code implementation in Rust. The author of the Go implementation, Filippo Volsoder, also created a TypeScript-based implementation, so if you want to do something in the browser, or maybe you're doing a Node.js backend, something like that, that's an option. Again, on the right side, less familiar, I will call out the Kotlin version, Cage, that has a few more dependencies. It's actually integrated in this Android password manager, so that's where that came out of. That's available. And WebAssembly is another interesting one because there's a few, proof of concept, ageonline.com, using WebAssembly. So, of course, there's always inherent questions about the security of something in browser, but the idea of WebAssembly being you can do those crypto operations and it's only local in the browser. It doesn't actually pass the data to the server to do those encryption operations, which of course undermine the security of it completely. There's Passage, again, getting a lot out of the Age or Age name, depending on how it's used. But that's a fork of the password store tool that, again, the author of the Go reference implementation created using Age as the backend instead of GNU PG. Another one to call out is SOPS, the Secret Operations Editor. So this is handy for DevOps kinds of tooling where you want to have declarative configurations, whether YAML, JSON, TOML, etc. You can encrypt field values, but maintain your parsable structure. And so it's something I've played around with. I'm not super familiar, but it has pluggable backends, Aage, GPG, others. And of course, the one that's most interesting to me, the one I worked on, Apache NiFi processors. So just a quick highlight, there's two rather generically named, but encrypt content Aage with public keys or decrypt content Aage with private keys. Of note, you can, and I'll show the demo, you can configure the keys directly in the processor, which, like all other sensitive properties in NiFi, those get stored, encrypted locally. Now, normally if you're doing something at the enterprise level, you want to keep your secrets in some kind of secret store. So NiFi provides a pluggable parameter provider extension point, which integrates with all the cloud providers, HashiCorp Vault, 1Password, and it's an extension point so you can write your own. There you can keep the keys or any other sensitive values in your secrets manager, do access control, all the things you want to do for an enterprise kind of deployment. And these processors were released in NiFi 1.24.0 and the milestone 1 of the 2.0 release back end of last year. So it's been out there for a little while now. And these build on the Jagged implementation. So with that, again, just summarizing the capabilities there, Aage has an open standard. You can go read it, implement it, using only modern algorithms, and having those streaming capabilities. So I'm going to switch over and I'll do a short demo of what this looks like in NiFi. If you've never seen NiFi before, you've got a visual web interface for building a data pipeline. This one is very contrived. It's basically a self-looking ice cream cone of read the data, encrypt it, and then decrypt it. But it shows the processors and gives an opportunity to see where those configuration bits end up. So the encrypt content Aage processor, if you do view configuration, basically have three properties. You have the file encoding, so whether you want to write it out as the binary form or the ASCII armored form. You have the public key source. This can either be direct properties in the processor, or you can also reference a file on the file system. And then you have, in this case, since the source is properties, you have the value itself. And I'll get back to this in a moment, but this actually comes from a parameter reference. And it's not shown. Once you save the value of any sensitive property in NiFi, it's no longer exposed to the user. So there's that initial security exchange, and then any subsequent users only see that sensitive value set string. Then on the decrypt side, as you might imagine, very similar. In this case, there's only two properties, the private key source and the values themselves. The processor is able to read the header, read the first few bytes of the file to determine whether it's base 64 encoded or whether it's the binary form. So you don't have to configure it. It's able to do basically content type detection. The last configuration point, I mentioned the parameter providers. In this case, I haven't hooked in this demo flow to a parameter provider, but just using the local parameter defined capability in NiFi. Close that. So you can create a parameter context, which is basically a collection of one or more keys and values, keys in terms of property names and values. And then you can reference them in n number of components. So I've created this Aage keys parameter context. Go to here, I give the name, the private key, the public key, and then provide the actual value. And you can see over here the processors, or in this case just the one, but where that's referenced in your flow configuration. So it provides that abstraction and provides a way to quickly then link back to where that's referenced. So lastly, I've got a couple files on the file system. So this get file processor, all it does is read a directory, in this case something in my home directory, input files, and it's not filtering, it's just going to take whatever's in there. So I've got two sample JSON files, one large, one small, and I have the encrypt and decrypt content processors enabled, so it already processed through. One file is only, it's less than a kilobyte, the other is a couple, over 100 megabytes. So we can actually then take a look at what happened to the files through the system. So if you go to view data provenance, You can see the time, the operation, content modified, so of course going from unencrypted to encrypted. And then if we go into the details, I'm going to look at the small one so it's actually visible. You can see what happened in terms of here's the file attributes, shows the file name, time, those kinds of things. And you can actually drill into the content. So we have the input claim, the file as it came into the processor, and the output claim, the file after it left the processor. So we can do view here, and oh, that's too old already. There we go. So that's the input. Let me bring up the other one for output. Okay. All right, so input, this is NiFi as a standard content viewer to give you some sense of the data. The generic hex viewer, so no matter what the data is, this will always work. So you can sort of tell it's JSON. In this case, since we know it's JSON, we can switch and view it as JSON, or we could if it was available. It's already aged off. I'll switch back. Then the output, the encrypted. So here you can see that header, again, the semi-human readable, at least the ASCII encoded part, followed by the binary encrypted payload. So again, like most encryption demos, there's not a lot of excitement. Hey, it looks like a blob of unintelligible goo, but you can take the word for it and you can look at the implementation. So with that, I'll summarize back again. If you want to take a look at the code, it's on GitHub. I actually, finally after developing it and going through several iterations, got a few issues back over the last year. This morning I decided to go ahead and release version 1.0.0 in light of the conference, so it's available on Maven Central as well. And again, if you're interested, I have a couple blog posts on Auge itself and the NiFi implementation on exceptionfactory.com. So thank you for your time, and if you have any questions, let me know.